Okay, so in the chapter Wave Optics, we discussed how it was discovered and proved that light has wave nature. Okay. So we know that light behaves as a wave from the interference diffraction experiments, and based on the fact that light can be polarized, they even concluded that light is a transverse wave, transverse electromagnetic wave. Okay. In this chapter, we will be looking at some experiments or some practical observations which cannot be explained by wave nature of light. If you treat light as a wave, you can't explain those observations. So that led to the discovery that light sometimes also has particle nature. You have to treat it as a collection of particles or packets. Okay, so those experiments are what we are going to discuss in this chapter. First, Hertz's observations. Now, Hertz used to conduct experiments on something called spark discharge. Can any of you explain how lightning occurs? How does lightning occur? Okay, I got an answer as a sudden discharge of electricity, that means electrons, okay, between high and low potential points. Correct, correct. So lightning is nothing but a spark, fine, a very strong spark between the clouds and the earth when there is very high potential between potential difference between them. Now, what exists between clouds and the earth? Air, okay, or atmosphere, which is usually a non-conductor. Okay. But when the electric potential difference becomes too high, a non-conductor also can turn into a conductor. Okay, it's something called dielectric breakdown. Fine. So suppose there are two electrodes like this, one of which is positive, the other is negative. Fine, means one is at high potential, the other is at low potential. When you create sufficient potential difference between them, whatever air is present between these two electrodes becomes a conductor. Okay, and you will see a spark being generated between them. That is basically nothing but transfer of electrons or ions. Depends on what exactly is present between the electrodes. Fine. So you see a spark getting generated between them. And this is what happens in a vehicle's spark plug also. To run a vehicle, it needs a spark plug. Basically, spark plug ignites the fuel inside the engine of a vehicle. Right? So spark plug keeps on doing this. It takes voltage from the battery, fine, and it generates a sufficiently strong electric field between two electrodes that whatever is present between those two electrodes gets ignited. Okay, due to that spark that is generated. Fine. So Hertz was conducting experiments on this spark discharge. Just a moment. Pradhan is asking, does this have something to do with dielectric constant of air? Definitely. Okay. Uh, when air will convert into a conductor depends on the dielectric constant. Yes. Okay. Yeah. So Hertz was conducting experiments on this spark discharge, and he observed that when the negative electrode, okay, is illuminated by UV rays, okay, when UV rays are incident on the negative electrode, he found the spark to get enhanced. Spark getting enhanced means what? More electrons getting transferred from the negative electrode to the positive electrode, more number of electrons undergoing that discharge. Right? Now, when will an electron jump out from an electrode? Okay, see here what is happening is electrons are getting transferred from the negative electrode to the positive electrode when there is sufficient potential difference between them. Okay. So basically, when you create a potential difference, you are creating a very strong electric field. And you know electric field will exert forces on the charged particles. Now both these electrodes are conductors. Conductors have something called free electrons. The free electrons of conductors are not absolutely free. Okay, they are free to roam around in the conducting material, okay, on the conducting surface, but they can't leave the surface. Okay. Why they can't leave the surface? You consider a conducting surface like this. Fine. What is this? Okay. Assume these are the free electrons which are free to roam around in the entire material, conducting material. Now, if one of these free electrons leaves the conductor, fine, you will automatically be left with a residual positive charge on the surface because conductor is normally neutral. If an electron leaves, you will be left with a positive charge, and that positive charge will attract the electron back. Okay. The electron will experience a force this way. So whatever we call as conduction electrons or free electrons, they are not absolutely free. They are only free to roam around in the conductor. They can't leave the conductor. But it is possible to pull out to pull out electrons from a conductor. Okay. All you have to do is provide sufficient energy to the electrons to overcome this attractive force of the metal surface. Okay. Whatever residual positive charge is there, if you give sufficient energy for the escaping electron to overcome that attractive force from the residual positive charge, it will leave the metal surface forever. Okay. That is called electron emission. Now, there are three different ways in which you can supply that energy for the electron to escape from the metal surface. Now, the minimum energy required to help the electron escape from the metal surface is what you call as its work function. A very important term in this chapter, phi naught. Okay, it's the minimum energy that an electron must be given, or that an electron must acquire to escape the metal surface. Usually, this is a very small amount of energy, and the common unit in which we express work function is electron volt, EV. Okay, this is a unit of energy. Can any of you define an electron volt? How much energy is 1 electron volt? Okay. See, whenever a charge Q goes through a potential difference of delta V, okay, what happens is the charge either gains or loses an energy of Q delta V. Okay, charge multiplied with the potential difference. If it goes in a favorable direction, it will gain that much kinetic energy. If it goes in the opposite direction, it will lose that much kinetic energy. For example, positive charges like to go in the direction of electric field. Okay, means they like to go from high potential to low potential. So when you take a positive charge from high potential to low potential, its kinetic energy will increase. But if you force it to go from low potential to high potential, its kinetic energy will decrease by the same amount. So when a charge Q goes through a potential difference delta V, then its energy, its kinetic energy increases or decreases by Q delta V. Okay. Now, if the charge is equal to that of an electron, that is 1.6 into 10 power minus 19 coulombs, and if the potential difference is 1 volt. Okay, if the charge of an electron is taken through a potential difference of 1 volt, then how much energy will it gain? The charge is E and the potential difference is 1 volt. This energy is what we call as an electron volt. Okay, so when the charge of electron charge is how much? 1.6 into 10 power minus 19 coulombs goes through a potential difference of 1 volt. Okay, this is what we call as 1 electron volt of energy. and you can convert it to joules also. 1 coulomb into 1 volt is basically 1 joule. So you can say that the left hand side of this expression 1.6 coulomb into volt is 1.6 into 10 power minus 19 joules. That is what is 1 electron volt of energy. Okay, you need to remember this is very useful. Remember the definition, you can derive this whenever you need. Okay, charge of an electron multiplied with 1 volt is what you call 1 electron volt of energy. And you can see it's a very small amount of energy, 1.6 into 10 power minus 19 joules. Usually, the work function of metals, what is work function? The energy that you need to supply to the electrons to help them escape from the metal surface. The work function of metals usually is around 2.2 to 5 electron volts. So it will be in the order of a few electron volts. That's all. That much energy, if you give to the electron, it can leave the metal surface. Okay. Well, there are other factors also. This is the minimum amount of energy required. There's no guarantee that every conduction electron will come out if you supply this much energy. Okay. For the first electron to come out, it is relatively easy. Why? When the first electron tries to jump out of the metal surface, there is only one positive charge left behind to attract it back. Okay. So it can overcome that attraction easily. Let's say the first electron has escaped. Now, if the second electron tries to escape from the metal surface, then what will happen? There will be two positive charges left on the metal surface. Then it will experience a stronger force of attraction. It will need more energy to escape from the metal surface. Okay, so not all electrons escape when you supply work function energy. Okay? Keep that point in mind. Okay, so if you somehow supply this energy work function, the electron can escape from the metal surface, and there are three different ways to supply this energy. Three different ways by which electrons can be taken out from metal surfaces. Okay. The first one is thermionic emission. As the name suggests, it is nothing but electron emission due to heat. You just heat the metal surface, the electrons will, at one certain temperature, the electrons will have sufficient energy to escape the attraction and to overcome the attraction of the positive charge and escape the metal surface. Okay, so basically this is electron emission due to high temperature. Another way in which you can get electrons out of the metal surface is by creating a very strong electric field. Okay. That is called field emission. You know, electric field can will exert force on charged particles. So if you create a sufficiently strong electric field, electrons can be pulled out from the metal surface. So basically field emission is electron emission due to a strong electric field. How strong is strong? It should be about the order of 10 power 8 volts per meter. Okay, very strong electric field is needed. Next, the third method in which you can get an electron out is by supplying energy to the electrons through radiation. Radiation, you can call it as light also if you want. So light energy has to be supplied to the electrons and they can absorb that energy and escape from the metal surface. That is called photoelectric emission. Photo referring to light or radiation. So when an electron receives that energy from radiation, it can escape from the metal surface. So this is basically electron emission due to energy from radiation incident on it. Okay. Now, when Hertz was performing experiments based on spark discharge, that is basically discharge of electrons from negative electrode to the positive electrode, he found that when UV radiation is incident, the spark discharge was enhanced, means more electrons were coming out from the metal surface. Okay. So what do we conclude from this? It can be concluded that UV radiations are somehow helping the electrons to escape from the metal surface. Okay, so electrons are able to absorb energy from UV radiations and use that energy to get out of the metal surface. That is what it means. Once the electron is out of the metal surface, okay, the potential difference between the two electrodes. See, there's a positive electrode and a negative electrode. Now, electric field will be from positive electrode to negative electrode. That's the direction of the field. And you know, electron experiences force opposite to the electric field. So once the electron is out of the metal surface, this electric field will pull it from one electrode to the other electrode. And as the electron moves from one electrode to the other, it passes through a gas. Fine. So electrons will undergo collisions with the gas molecules, and that is what generates heat or that spark. Fine. So you may not observe this in vacuum. Lightning also is the same thing. There is a sudden discharge of electrons between the cloud and the earth, and they have to pass through the atmosphere. Okay, particles in the atmosphere. So when they undergo collisions, they generate a lot of heat and light. So based on Hertz observations, it can be concluded that radiation is somehow helping electrons to get out of the metal surface. Okay. Next is Hallwachs and Lenard's observations. Hallwachs and Lenard, basically they conducted proper experiments on this photoelectric emission. What they did is they took a discharge tube. Okay, discharge tube is basically a gas tube which is evacuated. Evacuated means nothing present inside it, no gas present inside it. So they took a discharge tube with two electrodes. Just a moment, I'll copy the diagram. Okay. So they considered a discharge tube. This tube that you see is what you call as a discharge tube. It has two electrodes at the opposite, facing each other at the opposite ends. And there is a facility for radiation to be incident on one of the electrodes through the quartz window. Okay. Now you complete this, like connect the electrodes to a voltage source. Or you can consider a milliammeter. Fine. Now see, you just take an evacuated glass tube. Evacuated glass tube means there are no gas molecules also inside it. It's completely vacuum. And assume the source is not switched on yet. The radiation is not switched on yet. Now what will happen? Even if you close this switch, okay, the circuit is not complete. Okay, you have applied a voltage, okay, or a potential difference. There's an ammeter also connected, but it's not a closed circuit. So you can't expect current to pass through this ammeter. Okay, so reading will be 0. But it was found that when radiation is incident, okay, on the negative electrode, we call it as emitter plate. The opposite one is called the collector plate. When radiation is incident on the negative electrode, it was found that the current is non-zero. Now, how do we explain that? We have created a potential difference, that's fine. You can see that positive terminal is connected to A, positive terminal of the battery is connected to A, negative is connected to C. If positive is connected to A and negative is connected to C, then there will be an electric field from A to C. If electric field is from A to C, electrons will experience a force from C to A. Okay. And if an electron actually moves from C to A, then it will flow through the rest of the circuit also. That is how current can be detected by the ammeter. So they found that when radiation is incident on the emitter plate, the current is non-zero, and that can only be explained in terms of electrons, or by assuming electrons are somehow getting transferred from the emitter plate to the collector plate. Okay. So the radiation is helping electrons leave the emitter plate, and then the potential difference that we applied here, okay, is helping the electrons move from emitter plate to the collector plate and complete the circuit. So Hallwachs and Lenard, what they did is they conducted experiments based on this. Okay, and this is the proper experimental setup that they used. So there is a source of voltage, as you can see, and there's an ammeter, microammeter, because the currents are expected to be very, very small. And there's something called a commutator here. What does a commutator do? It helps you switch the terminals. Okay, if you want, you can maintain this side at high potential and this side at low potential. Or by switching, you can even maintain this side at high potential and the opposite side at low potential. So that facility was there. Right? So these are the experiments which actually made them doubt the wave nature of light, and which made help them discover the particle nature of light. Now, what all did they observe? First one, can any of you recollect and tell me the observations based on photoelectric emission? Okay, fine. So the first, what do you say? The first parameter that they considered was intensity of radiation. So what they did was they kept the other parameters constant, means the applied voltage, they kept it constant. Frequency of radiation, they kept it constant. Okay. They only varied the intensity of radiation. Right. And it was found that as intensity increases, the photocurrent, okay, they call the current through this ammeter as photocurrent. Why? Because this current is arising from photoelectric emission. So they called it as photocurrent. It was found that when intensity of radiation, capital I, is increased, small I, the photocurrent, increases proportional to it, directly proportional. Okay, so the graph between photocurrent and intensity was found to be a straight line. Fine. So what can we conclude from this? It was found that if you increase intensity, current is increasing. Now, current increasing means what? Number of electrons emitted per unit time increasing. If more electrons are emitted, obviously that will lead to more current. Okay. So what we can conclude based on this is that the number of electrons emitted is proportional to intensity of radiation. Okay. But they observed one more thing also. See, uh, they varied the intensity by keeping frequency constant, frequency of the radiation constant. So at one frequency, okay, let's say the frequency corresponding to red colored light or violet colored light. Okay, violet color has more energy, more chance of electron emission, or UV light also you can take. They fix the frequency and they vary the intensity. They record the graph. Then they repeat the experiment, okay, by fixing another frequency, a higher frequency or a lower frequency, and varying intensity again. Okay, so they performed experiments at different frequencies. Fixed frequency, varying intensity, another fixed frequency, varying intensity. That is how they do the experiments. They found that below a certain minimum frequency, no photoelectric emission was observed, irrespective of how much the intensity is. Okay, so this is one observation, that number of electrons emitted is proportional to intensity of radiation. Another observation is that there is no photoelectric emission if the frequency of radiation is below or less than a certain minimum frequency, irrespective of intensity. When the frequency is too low, how much ever intensity you put, you are not going to observe photoelectric emission. This minimum frequency is called threshold frequency. Denoted by the symbol nu naught. Okay. Only if frequency is equal to or greater than the threshold frequency, then based on intensity, the current was found to increase or decrease. Okay. The next observation is how the photocurrent varies based on the potential that is applied. Okay, let us take the circuit diagram. Okay. Now, suppose A is kept at high potential. Okay. The collector plate is kept at high potential and emitter plate is kept at low potential. Then what will happen? The electric field will be created from A to C. This is the direction of electric field. Then the force on the electrons will be this way towards, like from C towards A. That will be the direction of force on the electrons. Now, if electrons are forced to go from emitter plate to collector plate, C is the emitter, A is the collector, then it will help in completing the circuit. It will help in producing more current. Okay. And one more thing is, when radiation is incident on the emitter plate, the electrons that are emitted, they don't have to come out in one direction only. They don't have to have a velocity in the same direction. Different electrons can have velocities in different directions. One electron may come out of the metal surface in this direction. Some of them may be moving directly towards A also. So when you create an electric field like this, what happens is you will force the electrons to turn towards the collector plate. The electrons which are emitted in random directions will be forced to move towards the collector. So the stronger this electric field, greater will be the number of electrons going from the emitter to the collector. Okay, instead of going in random directions, they will prefer to go towards the collector if this electric field is strong. Okay, so when the collector, that is A, is kept at high potential and the emitter is kept at low potential, we call this as positive voltage. Okay, or you can say positive collector potential. When the collector potential is positive, means when collector is at high potential, it was found that as you increase the potential, okay, on x-axis we have potential, collector potential. On y-axis we have the photocurrent. Okay. As you increase the collector potential, the current increases, photocurrent increases, because electrons which are uh, emitted in random directions are also forced to move towards the collector. So that will increase the amount of current in the circuit. But once you apply a field which is strong enough to direct all the electrons to go from emitter to collector, once the field is strong enough to make all electrons go from emitter to collector, after that, even if you increase the field, there are no stray electrons to be directed towards the collector. Okay. So as you increase the voltage, the collector voltage or collector potential, you will see that current rises up to a certain level and then it stabilizes. Okay. That is called saturation current. Why is it getting saturated? Once all the emitted electrons are directed towards the collector, after that, even if you increase the voltage, there are no stray electrons to be directed towards the collector anymore. Okay. So current cannot increase any further. So only up to a certain voltage current was found to increase. After that, it won't increase. Fine. And even when the applied voltage is zero, even when collector voltage is zero, some photocurrent was found to be observed. All this happens only when frequency is greater than or equal to the threshold frequency. Okay. Even when there is no collector potential applied, some of the electrons will definitely be moving towards the collector, no? So that will lead to completion of the circuit and detection of some current. Okay. What if the terminals are switched? If the terminals are switched, Okay, you keep the emitter at high potential, collector A at low potential. Then the electric field will be to the right. If electric field is to the right, the force on the electrons will be to the left. What this force will do is it will prevent, or it will try to prevent, electrons from reaching the collector. It will uh, oppose completion of the circuit. So as a result, what will happen? The current should decrease, and that is what was observed. For for negative collector potentials, okay, the current was found to decrease, and at one particular potential, the current even becomes zero. This negative collector potential at which the photocurrent becomes zero is called the stopping potential. Very important term in this chapter. Okay, so basically when you switch the terminals, no, when you make collector low potential and emitter high potential, the electric field generated will prevent the electrons from going to the collector. It will oppose the photocurrent. And when it is strong enough, it can stop the photocurrent altogether. So basically it is the negative collector potential at which the photocurrent becomes zero. Now, photocurrent becoming zero means what? All electrons being successfully prevented from reaching the collector. So you can say that stopping potential is the potential required to prevent or to stop, potential required to stop the most energetic electron from reaching the collector. If the most energetic electron is prevented from reaching the collector, then all other electrons will definitely get prevented. Okay, so that potential needed to do that is what you call stopping potential. Fine. So when this experiment, which studied current as a function of potential applied, was conducted at different intensities, it was found that only like say they'll fix the intensity, they'll fix the frequency, they'll vary the potential and study the current. They'll get one graph. Okay, the experiment can be repeated at a different intensity. Okay, so let's say the intensity was increased and the experiment was repeated. It was found that when intensity is increased, the saturation current increases. Okay, so let's say this graph was obtained at one intensity I1. Then at another intensity, let's consider a higher intensity, it was found that the graph goes like this. There is a higher saturation current when intensity is increased, I2 greater than I1, but the stopping potential stays the same. Okay, what does this help us understand, or what can we conclude based on this? If you are increasing intensity, the number of electrons emitted is increasing, but the energy with which each electron comes out is not increasing. The stopping potential remained the same. Means what? The potential required to stop the most energetic electron is still the same. Means the electrons are still coming out with the same amount of energy. Okay, so therefore it was concluded that intensity has nothing to do with the energy of electrons. Okay, so at different levels of intensity, they conducted the experiment. They studied how current varies with potential, and it was found that stopping potential remains the same irrespective of intensity of radiation. Okay. Next, they repeated the same experiment. Means they studied current as a function of voltage, but at different frequencies this time. Okay, different frequencies of incident radiation. And what they found was interesting. So, okay. Now, all the frequencies, okay, nu1, nu2, or how many ever frequencies they used, they must be greater than or equal to the threshold frequency. Okay. Photoelectric emission should happen. Only then they can study how it depends on frequency. So all chosen frequencies are above the threshold frequency. So at one particular frequency, they got a graph like this. Fine. What graph is this? Current as a function of collector potential. And for that frequency, let's say nu1, this is the stopping potential. At that potential, the current becomes 0. Okay. Then they increased the frequency of incident radiation and repeated the experiment. What they found was, when frequency of incident radiation is increased, the saturation current does not change. See, this is the saturation current. If you increase the frequency, the saturation current does not change, but the stopping potential changes. So at another potential, when the experiment is conducted, not potential, sorry, at another frequency when the experiment is conducted, they found the graph to be like this. When frequency is increased, nu2 greater than nu1, the stopping potential increased. Okay, see, stopping potentials are negative potentials, that's fine. We are talking about the magnitude. A stronger negative potential was required to sorry, a stronger negative potential was required to make the current 0. Can any of you tell me what can be concluded from this? When frequency is increasing, the stopping potential is increasing. What can we conclude from this? I got one answer as, is it because more electrons are put out per unit time? See, if more electrons are released per unit time, current should increase. Stopping potential is increasing. You have to think of what stopping potential depends on. Then you can explain, then you can conclude something from this. The stopping potential is the potential required to prevent the most energetic electron from reaching the collector. Fine. Now, when frequency is increased, it is found that more potential is needed to stop the electrons. What does that mean? Electron energy is increasing. Okay. So from this, we can conclude that the energy of electrons, the energy of emitted electrons depends on frequency of incident radiation. See, questions based on these graphs are very common. Okay. They can just give you a graph and ask you which frequency is more or which stopping potential is more. Fine. So you need to know what exactly happened in the experiment. Okay. What exactly was observed in the experiment. Okay. Right. So these were the fundamental observations that they made. First is that, or in all cases, the frequency was kept more than the threshold frequency. And the first observation is that the intensity of radiation, when it was varied, the current varied proportional to intensity, means more intensity led to more electrons being emitted. Okay. Next, effect of the collector potential. As you increase the collector potential, current increases up to a certain maximum level called the saturation current. And when you reverse the potential, at one certain potential called the stopping potential, current becomes 0. And stopping potential was found to be independent of intensity. Okay, that is the main thing here. Means the energy of electrons does not depend on intensity. Number of electrons depends on intensity. Energy does not depend on intensity. Energy depends on frequency. That's the third observation. Pradhin is asking, so higher energy light gives higher energy electrons. Yeah, correct. Frequency is more, then energy of incident radiation is more, then energy of electron is more. So that is how they connected it actually. Okay, that yeah, radiation energy is more means electron energy is more. Fine. Now, suppose light is a wave. Now, what is a wave? Wave is a continuous distribution of energy, right? So let's consider a metal surface here. Assume there are electrons. These are free electrons, okay, which are on the metal surface. Okay. Let's say radiation is incident in the form of a wave. If light was actually a wave only, then even if the frequency is too low, okay, or irrespective of what is the frequency, see, frequency is less, definitely the what do you call, energy of radiation will be less, right? But even at low frequency, if the radiation is incident for sufficient amount of time, then the electron should get sufficient amount of energy to leave the metal surface. See, low frequency waves have low energy. That's fine. But if you make it incident for a lot of time, then you should be supplying sufficient amount of energy, no? Okay, that's the idea. So even if the frequency is below the threshold frequency, if the radiation is incident for a longer amount of time, we can expect the electron to attain sufficient energy and leave the metal surface. But this was never found to happen. Okay. If frequency is less than the threshold frequency, electron emission is never observed from that particular metal. Okay, irrespective of how much ever time you allow the radiation to be incident. So definitely this is contradicting the wave nature of light, because wave is a continuous distribution of energy. If waves are incident for a lot of time, a lot of energy will be incident. Okay, then eventually the electron should come out, but it never came out. Next observation. If the frequency is greater than the threshold frequency, electron emission was immediately observed. Okay, within nanoseconds, you can say. The moment radiation is incident, you will see electrons coming out of the metal surface. Now, suppose the frequency is just above threshold frequency. Still, for the electron to attain the required amount of energy, it should take a little bit of time. Or if frequency is more and more increased, okay, above the threshold frequency only, as frequency is increased, the electron should take different amounts of time to come out. Because if frequency is above threshold frequency only, let's say just above threshold frequency, then it's the bare minimum frequency that you are giving. Means bare minimum energy per radiation. Then it should still take some time. Let's say, uh, okay, I can't actually quantify. Let's say a time t1 is needed for electrons to come out when the frequency is just equal to the threshold frequency. Now, when you take frequency significantly higher than the threshold frequency, let's say 10 times of threshold frequency, then basically you are making stronger radiation incident on the electrons, more high energy radiation incident on the electrons. Then in a time less than t1, the electrons should get emitted. But it was found that once the frequency is beyond threshold frequency, irrespective of what frequency is incident, electron emission happens at almost the same time. Okay, so electrons don't wait to attain sufficient energy from the waves. Okay? For a wave to supply energy to the electron, it takes time. Okay, wave is a distribution of energy. For all that energy to fall on the electron or to go to the electron, it takes a little bit of time. But it was found that photoelectric emission is independent of time once the frequency is more than threshold frequency. This also led them to doubt the wave nature of light. Okay. Next, I think this much is enough. to doubt the wave nature of light. Intensity increases. Okay, yeah. They also observed, Hallwachs and Lenard in their experiments, they also observed that stopping potential was independent of intensity. Stopping potential is the potential required to prevent the most energetic electron from reaching the collector. Okay. Now, generally what should happen if intensity of radiation increases? Okay, suppose frequency is more than threshold frequency, you increase the intensity of radiation. In terms of waves, higher intensity means higher amplitude of the wave, means more energy per unit length in the wave. Each pulse will have more energy. For example, let's say this is one wave having a low amplitude, and this is another wave having higher amplitude. Higher amplitude means higher energy per pulse. Okay. Then what should happen? If you increase intensity, electron should receive more energy and come out with a higher amount of energy had light been a wave. Okay. Had light only been a wave, higher intensity should have resulted in higher amount of energy in the electrons. But even if intensity is increased, stopping potential remained the same. Means electron energy is independent of intensity of the waves. This also made them doubt the wave nature of light. Okay, so not doubt, actually, it contradicted the wave nature of light altogether. Okay, so there had to be another way of looking at light, not only as a wave. Okay, that is when Einstein came into the picture and proposed Einstein's photoelectric theory. Okay, what did Einstein say? Einstein said that light is not always a wave. When interacting with particles like electrons, very, very small particles like electrons, light behaves as a stream of particles. Okay, you have to consider light as a stream of particles to be able to explain all these observations. And these stream of particles, light particles, are called photons. Okay, so he said light is a collection, or light behaves as a stream of photons. Okay. A photon, he proposed this idea of a photon. Photon is a packet of light energy. Okay, how much energy does each photon carry? Energy of a photon, he said, is h nu, where h is Planck's constant and nu is the frequency of light. You can also write it as hc by lambda. Okay, they carry this much energy. Each photon carries this much energy, and it depends on the wavelength or frequency of the radiation that is incident. And he also said that electrons carry, not electrons, sorry. He also said photons carry momentum. Momentum of a photon is the energy of the photon divided by the speed with which it is traveling, E by C. So hc by lambda divided by C, you can write it as h by lambda. Okay. So each photon, that is each particle of light, carries this much energy with it and this much momentum with it. Okay, so he proposed this idea of photons. Okay, let's solve some basic problems based on this. There are some other postulates also in this Einstein's photoelectric theory, but just based on energy of photon and momentum, let's solve some problems. First, suppose n photons, small n number of photons, strike a surface per unit time perpendicular to it and are absorbed by the surface. Okay, n photons, each of frequency nu. Okay? Photon frequency is nu. Now photons carry momentum. When anything carrying momentum strikes a surface, it transfers that momentum. Okay, or it transfers some momentum to the surface. So it exerts a force on the surface. So n photons of frequency nu strike a surface per unit time perpendicular to it and are absorbed by it. Calculate or derive an expression for the force acting on the surface. Do this all of you, I'll give you 2 minutes. Can one of you tell me how force is related to momentum generally? How is force related to momentum? Or what is Newton's second law?
The force is dp by dt.
Correct, rate of change of momentum. Fine. So suppose this is the surface and let's say these particles called photons are striking the surface perpendicular to it and they are getting absorbed. Photons are getting absorbed means all the momentum of the photon is being given to the surface. Okay. So let's say each photon carries a momentum p. Then all the momentum p will be delivered to the surface. The photon loses its momentum. Surface gains that momentum. That's all. Now, one photon carries a momentum of h nu divided by c. Energy is h nu, momentum is h nu divided by c. That's like c need not be given in the question, h need not be given in the question. These are universal constants. Okay, frequency was given. So this is the momentum of each photon. Okay. So whenever one photon strikes the surface and gets absorbed by it, this much momentum is received by the surface. Now take a time delta t or consider an interval delta t. Now in that interval delta t, assume capital N number of photons strike the surface. Okay. See, if you want, you can take unit time itself. You can take an interval of 1 second. Okay. And they have given you in the question how many photons strike per second. You can solve it that way also, solving it this way. So in an interval delta t, let's say capital N number of photons strike. That means the total momentum delivered to the surface will be capital N times of momentum of each photon, h nu divided by c. And this delivery happened in how much time? Delta t. So this will be the force acting on the surface. Momentum delivered to it divided by the time in which it was delivered. And n is the number of photons, t is the time. So capital N divided by delta t is the number of photons per unit time, which was given in the problem as small n. That's all. Therefore, the answer for force acting on the surface is small n h nu by c, where c is the speed of light in vacuum. Is this clear to all of you? Any doubt in this? Just think of the relation between force and momentum. Based on that, you can tell how much force acts on the surface. Now here, we assume the photons are absorbed by the surface. Now it is also possible that surface reflects photons. Okay. Just tell me how the answer will vary or how the solution will vary had the photons been perfectly reflected by the surface. Suppose the surface is a perfect reflector. Then how much force will act on it? We had discussed something similar in electromagnetic waves also when we talked about radiation pressure on a surface. If the surface is a perfect absorber, there'll be a certain amount of pressure on it. If it's a perfect reflector, there'll be a certain amount of pressure on it. Think about it, all of you. If the surface is a perfect reflector, how much force would have acted on it? Okay. What difference does the nature of surface make? Whether it's a perfect absorber or a perfect reflector. Now, if it's a perfect absorber, the momentum of the photon will be lost and that will be transferred to the surface. But if it's a perfect reflector, okay, the momentum of the photon is not simply lost, it gets reversed. Okay. So consider one photon going with a momentum p towards the surface. If the surface is a perfect reflector, no, the photon will come back with the same momentum p in the opposite direction. So you should call it minus p. As a vector, if you take it, it is minus p. Now, if it's a perfect absorber, all the p of the photon is gone. But if it's a perfect reflector, the p of the photon becomes minus p. That means the change in momentum of the photon whenever it collides with the surface, okay? Whenever it strikes the surface, the change in momentum of photon is 2p. That is 2 h nu by c. If the momentum is simply lost, change is h nu by c. But if the momentum is becoming negative, then the change in momentum is 2 h nu by c in terms of magnitude. Okay, with direction, if you want, change in momentum is nothing but final momentum minus initial momentum. So that becomes minus 2 h nu by c. Okay, but magnitude is 2 h nu by c. That's the change in momentum of the photon. The same amount of momentum will be given to the surface. Okay, photons follow Newton's laws. Okay? Like, sorry, I should not say Newton's laws. They follow the law of conservation of linear momentum, conservation of energy. Okay. So when the photon's momentum changes by minus 2 h nu by c, it means a momentum of plus 2 h nu by c is imparted to the surface. So when it is a perfect absorber, the momentum imparted to the surface is only h nu by c per photon. When it is a perfect reflector, the momentum imparted is 2 h nu by c, double momentum, in the same amount of time. Then that doubles the force. So in this case, the force acting on the surface will be small n h nu by c into 2, where small n is the number of photons striking per unit time. Okay, capital N divided by delta t, we wrote it as small n. So it'll be 2 times the force experienced in case it's a perfect absorber. Now in electromagnetic waves, when we talked about radiation pressure also, we talked in terms of this. Okay, we imagined a ball striking a surface, rebounding with the same momentum. Okay, so if it's a perfect absorber, the radiation pressure is I by C. If it is a perfect reflector, the radiation pressure is 2I by C. Why is the pressure getting doubled? Because the force is getting doubled. Okay, same idea we use here also. Hope this is clear to all of you. If you have any doubt, you can ask. So Einstein proposed this idea of photons, which are basically packets of light energy. And he said each of these packets has an energy of h nu or hc by lambda and a momentum E by c, that is h by lambda, or h nu by c also you can write. Okay. Next. Basically, Einstein came up with ideas which explained Hallwachs and Lenard's observations. Okay. What were the observations? The first thing was that when intensity increased, the photocurrent increased. Okay. And when frequency is less than threshold frequency, there is no emission at all. Okay. So how did Einstein explain all these? He said that if frequency of the photon is below the threshold frequency, it means the photon has very less energy. Energy with it. Okay. Einstein proposed this idea that each electron can only absorb one photon. It can only accept a photon. Okay. And electron accepts a photon only when its energy is more than the work function of the metal. Okay. Now, how an electron decides to do that, or how an electron actually accepts electrons which are only of high energy and not of low energy, is not a part of your syllabus. You'll need to study quantum physics to understand all that. Okay, it has been explained. There is a proper theory for it, but as of now, you don't have to know. But just know the ideas that he proposed. He said that electron will accept a photon only if it has sufficient amount of energy. Okay, and the same observation is seen in like we'll discuss in the next chapter also, atoms. When electrons jump from lower orbits to higher orbits, they only accept those photons which will enable them to go to a higher orbit. They don't accept all radiation that is incident on it. That is what gives rise to atomic spectrum. Okay, spectral lines. We'll discuss that in atoms also. So electrons somehow have this ability to choose which photon to accept. Okay, so if the photon's frequency is less than the threshold frequency, or you can also say like this, if the energy of the photon is less than the work function of the metal surface, electron does not accept that photon. Okay. So which observations could Einstein explain based on this? One thing, when frequency is less than threshold frequency, no photoelectric emission is observed. And another thing is that it is independent of time also. How much ever time the radiation is incident, and whatever be the intensity of radiation, if frequency is less than threshold frequency, no photoelectric emission ever happens. Okay? So that he could explain based on this. The photons are low energy photons. Electrons don't accept those low energy photons. Okay. Next. When intensity is increased, the energy per electron is not increasing, because when intensity was increased, stopping potential did not change. What changed? Saturation current changed. Okay, means more number of electrons were being emitted. So how Einstein explained that is, intensity of radiation is proportional to number of photons that are incident on the metal surface, not the energy of photons, but the number of photons. Okay, and that is how he explained that when intensity increases, number of incident photons increases, means the number of electrons which receive energy also will increase. No, there are more photons giving energy to the surface, then there will be more electrons taking energy from them and coming out. Okay? So intensity is proportional to number of photons, and that is how more electrons are emitted. So higher intensity means higher number of photons being incident. Okay. So energy of photon, stopping potential. Yeah, next thing is stopping potential. If intensity is kept the same, but the frequency of radiation is increased. Okay, all frequencies above threshold frequency only. As frequency is increased, what did Hallwachs and Lenard observe? They observed that stopping potential increases when frequency increases. For low frequency, the stopping potential is less. For higher frequency, the stopping potential is higher. Means when frequency increases, the energy of emitted electrons is increasing. Now, where is electron getting the energy from? According to Einstein, it is getting the energy from the photon. When frequency is increased, electron energy is increasing, means the photon energy must be increasing. Okay, so higher frequency means higher energy photons. So energy of photon, okay, that we have discussed anyway. There's a formula for it. Energy of photon is proportional to frequency of radiation. E is equal to h nu. So this way he could explain why higher frequency is giving higher energy to the electrons. Okay. And what if the photon, see, each electron accepts one photon, that's fine. And it accepts a photon if the photon has more energy than the work function. If the photon can help the electron escape the metal surface only, it will accept. Suppose the work function of the particular metal is 3 electron volt. But let's say the photon carried an energy of 4 electron volt. Now, photon is having more energy than the work function, so it can help the electron get out of the metal surface. Now, electron takes all these 4 electron volts. Okay. When it accepts a photon, it has to accept all the energy that it brings with it. So electron takes the 4 electron volt energy. How much energy is needed to overcome the attraction of the metal surface? 3 electron volt is sufficient. It uses or it spends that 3 electron volt to get out of the metal surface. It will still be left with 1 electron volt of energy. What will happen to that 1 electron volt of energy? It appears as the kinetic energy of the emitted electron. So this is what leads us to Einstein's photoelectric equation. In the best case, okay, suppose there is no other loss of energy happening from the electron, and suppose the electron just requires the work function amount of energy to get out of the metal surface. See, I told you at the beginning of the class, not all electrons can come out when you supply the work function energy. Some electrons can, some electrons cannot. Okay, and when coming out of the metal surface also, electrons may undergo collisions or something like that. So suppose the electron just requires the work function amount of energy to get out of the metal surface, and there are no collisions or anything. That's the best case. In the best case, the maximum kinetic energy with which an electron can come out of the metal surface is the energy that you supply, that is energy of photon, minus the energy that the electron should spend to get out of the metal surface. That's the work function. Okay, so we call this as Ke max because this is the best case scenario. Not every electron will come out with this much kinetic energy. Okay, only few electrons will be lucky enough to get out with this much kinetic energy. And this is theoretical only. Practically, there may be no electrons coming out with this much energy also. Okay, so Ke max, the maximum possible kinetic energy with which an electron leaves the metal surface, is the energy of the incident radiation h nu minus work function phi naught. You can write the equation like this. You can write the equation like this also. H nu minus H nu naught. Okay, where work function energy phi naught is equal to H into nu naught. Nu naught is the threshold frequency. Okay. So for a certain frequency of incident radiation, okay, this nu is frequency of radiation incident, right? This is the highest possible energy with which an electron can come out. The potential, the negative collector potential required to stop this highest energy electron is what you call stopping potential. Okay, Pradyun, just a moment, I'll take your doubt later. So this expression h nu minus h nu naught or h nu minus phi naught gives you the maximum possible energy with which electron can be emitted at a particular frequency. Now, the potential, the negative collector potential required to stop this electron is what we call as stopping potential. Okay. Therefore, we can say that Ke max, okay, the energy of the most energetic electron, the kinetic energy of the most energetic electron is equal to charge of electron multiplied with the stopping potential. Basically, we are using the idea that when a charge Q goes through a potential difference delta V, it either gains or loses a kinetic energy of Q delta V. Okay. Now, we want the electron to be stopped. We want this most energetic electron to be stopped. And it is found to get stopped when it goes through a potential difference delta V. So, when a charge Q goes through potential difference delta V, the kinetic energy it loses or gains is charge multiplied with the potential difference. So, this is how stopping potential is related to kinetic energy of the electrons. Okay. So, E into V naught is equal to Ke max. That is H nu minus H nu naught. Okay. Questions based on this equation are also very common. How stopping potential depends on frequency of radiation. The graph will be a straight line. What is the slope of that line? What is the intercept of that line? You can also write this as Hc by lambda minus work function. So they may ask you how stopping potential depends on wavelength of radiation incident, what the graph will be like. So graphs based on Einstein's photoelectric equation and problems based on it is what we will discuss in the next class. Okay. This is a simple chapter. So today's class, what we discussed is some observations which which led scientists to doubt the wave nature of light. Okay, in fact, some observations which contradicted the wave nature of light are what we discussed, and how Einstein explained these observations by proposing the photoelectric theory. So he proposed this idea of photons, okay, which are basically packets of light, energy of photon, momentum of photon, all that we discussed. And what is happening in the photoelectric experiment also, he explained. So each electron accepts only one photon, and electron has the ability to decide whether to accept a photon or not. And it accepts the photon only if it can supply enough energy for the electron to get out of the metal surface. Okay, so only high energy photons or sufficiently energetic photons are accepted by electrons. Okay, what if the photon brought more energy than required? That excess energy appears as kinetic energy of the electron. So maximum kinetic energy with which electron can get out is energy of photon minus the energy it needs to spend. That is the work function. Okay, fine. We'll stop it here for today. We'll continue in the next class. Just a moment.